Welcome back. We're going to look at forces in motion right now. The units of forces were named after Isaac Newton to honor him, and so they're just called newtons, or capital N for short. And other than his laws of motion, one of them in particular determines a lot of how forces influence motion. That's his second law, that the force net, or the net force rather, equals the mass times the acceleration. And so we can say that any unbalanced force, that is to say forces that do not cancel each other out completely, are going to cause acceleration. So unbalanced forces could be acting in opposite directions like this, and let's say this one is 20 newtons and this one is 10 newtons. I would have a net force, or overall total force, acting in the upwards direction by a magnitude of 10 newtons. Okay? And this would be what creates acceleration. An unbalanced force, on the other hand, does not cause acceleration. Or excuse me, a balanced force, on the other hand, does not cause acceleration. Said that backwards. So if we had 10 newtons and 10 newtons, the net force is not a vector anymore because there is no net force. It is 0 newtons, which means no acceleration. Quick caveat here, no acceleration means no getting faster, no getting slower, and no changing direction. Nowhere in this does it say you cannot already be moving. Okay? A car, or UFO apparently, which is moving forwards with a constant velocity of 25 meters per second. That is not accelerating. Does not have a net force. That does not mean there are no forces acting on it, and it does not mean that it is not moving at all. If I drew the three-body diagram, I would have the force of gravity, or its weight, pulling it down into the ground. I would have the normal force exactly opposing the weight of the car. And remember, this is the push of the ground up. It's the reaction of the ground to the action of the car, Newton's third law. And the reason we know these are balanced is because the car is neither levitating spontaneously, nor is it burrowing into the ground. Okay? That would be pretty ridiculous. We know in a car, in reality, you also have to accelerate forwards to keep it going, otherwise it stops, even though Newton's first law says an object in motion will stay in motion, but that's not because of objects not wanting to stay in motion, it's because of another force that people tend to overlook, and that is the force of friction acting on the car. I'll just do that F sub FR. Okay. And the friction acting on the car is acting between the ground and the wheels. It's always opposing the motion of the car. And it's a little rolling friction that wants to make the car slow down. That's what friction does. So to keep the car going, you have a little forwards push from the engine. At a constant velocity, it would balance out. So you would look at this and might be tempted to say, oh, no net force, no acceleration, the car must be at rest. Well, that is a possibility, but not a certainty, because it could be moving at anything that is not 0. As long as it's not changing that, it's perfectly acceptable. Okay? The forces are balanced, it's not accelerating, but it's not changing its motion, is all that means. So it could be at rest, or it could be traveling along at 25 meters per second, it could be traveling along at 50 meters per second, it could be traveling along at any speed it pleases, so long as it's not changing that speed. And it's still true that it has balanced forces acting on it. Okay. So moving along, let me zoom back in here. The types of friction that are acting on objects are static friction, which means between a stationary object and the ground, or another stationary object, so objects that are not moving. For example, this ruler on my tabletop and on my paper here has static friction because it's not moving. If I were to slide it across my paper while it's moving, it has sliding friction between two surfaces which rub past each other. And in a car, or for example this marker that will come rolling down in a second, it has rolling friction, okay, between a rolling object and a non-moving, non-rolling object. The last kind is fluid friction, which for some reason people always get a little bit scared of, but it's not really anything hard. It's just that people tend to think of fluids as only liquids, and certainly there is fluid friction in a liquid. But by far the most common fluid friction which we talk about is not a liquid at all, it's a gas, and it's air resistance. So say that parachutist again. For the record, I would not jump with a parachute attached like this. That would be a recipe for decapitation, but this is a simple diagram. The air resistance, which pushes up against the parachute and results in this balanced force acting on the parachutist so that he can descend, or she can descend, at a constant rate, which is much, much lower than they would have without the parachute, is because of fluid friction. It's air that is filling the canopy of the chute and pushing up on the chute. And that push up on the chute pulls up on the parachutist, partially canceling out the downwards pull of gravity. And the only thing that makes this a fluid is the fact that it flows. If you push against a fluid, it goes around an object. And so we wind up with these weird looking pockets. So air is the most common kind of fluid friction when we're talking about planes, parachutes, missiles, rockets, all of these things. We're talking about drag. Okay? That air resistance is called drag. And it could be in water too, like if you have a boat, viewed from the top side, obviously, the fluid flows around the boat. That's all a fluid does. Flows around. And that flowing creates a resistance to motion that drags against the object trying to push through. And that's where that friction comes from. Okay. And just a quick word on strength, even though it's not in the review packet here. Static friction is the strongest, it's the hardest to overcome, so if you're stopped at a red light, it will take you more effort from the car, on the car's part, to get rolling than it will to stay rolling, because rolling friction is weaker than static friction, because there's already some sort of motion going on. Sliding friction is stronger than the rolling friction, but it's still weaker than static friction because it's already got motion involved. You don't have to start things moving. Okay. Another way to think of that is earthquakes. If my hands represent a fault line, and let me zoom out a little bit here, if my hands represent a fault line, they are pushing against each other for a really long time, and then suddenly there's a great big slip as the static friction is overcome, and it switches to a sliding friction. And that's what causes an earthquake to happen. That sudden slippage, that sudden overcoming of the opposing forces. Newton's laws of motion, I've stated them in a very succinct form on our review packet. Number one is simply inertia. Or you could say the tendency of an object to resist any change in its motion. So objects in motion stay in motion. objects at rest stay at rest. That is, unless they are acted upon by some outside force, which comes along and acts to change that motion. Second law is an equation. Force equals mass times acceleration, or the way he originally wrote it, acceleration equals force divided by mass, says that the acceleration is proportional to the force acting on a mass. Big forces equal big accelerations. Big masses equal slow accelerations. The third law is the one that gets very, very confused. The action-reaction. For every action, there is an equal and opposite reaction. And the main thing that people confuse on this one is that if I say I have a force of 100 newtons acting in this direction, people will want to say, if this is my action, then I'll draw a blue vector going in the opposite direction, so there's the opposite part, equal in size to the first, and that is my reaction force. It's tempting, but it's not actually true. In fact, action and reaction occur on separate objects. So if I have my original 100 Newton action force, my reaction force of 100 newtons in the opposite direction is on a separate diagram of a separate object pointed in the opposite direction but with the same size. This is the skateboard example that we did in class with the skateboards and ropes. Didn't matter if one person or both people pulled on the rope, both of the boards would always move experiencing the same exact force. Same thing with the scales. When you were pushing against them, one person push or both people push, didn't matter, the scales always said the same thing. Why? Because the action and reaction were happening on both scales at the same time. There was an action force and the reaction happened simultaneously in the opposite object. This means that they do not cancel, and both objects accelerate, but in opposite directions. And also according to Newton's second law. So if one of these objects is really big, so a really big m, then it's going to accelerate with a very tiny acceleration. If the other object is a really small m, it's going to have a really big acceleration. And this is for the same net force acting on them. For example, this 100 newtons. Okay? Same force acting on two different sized objects. The big one accelerates a little bit, the little one accelerates a big bit. This is why when you walk on the ground, okay, if I drew a foot here, to go forward, you actually push back. Feel free to test this if you want. You push back on the ground, so the force of your foot pushes backwards, and the ground pushes forwards on your foot, so the force of the ground pushing you forwards. These forces are not balanced, they do not cancel, and they result in you accelerating forwards in the direction of your net force, and the world accelerating backwards in the direction of its net force. The reason we don't really notice the world accelerating relative to us, because it's not just a big M, it's a huge M. It is a trillion times the size of your mass, and so it does not accelerate by very much at all. So you accelerate, and you notice that. The world accelerates, nobody notices that, because you're not putting a big enough force into it to actually see it. Rockets are another example. The rocket throws its propellant down. So there's the force of the rocket on the propellant, and the propellant acts against the rocket to push it up. Force of propellant on the rocket. This is why a rocket will still work in space, because if you say a rocket has to push off of the ground in order to go or have any motion, then once a rocket reaches space, it has nothing left to push against, not even air. And so a rocket should not work in space. But they do, because it's not the rocket pushing on the ground, it's the rocket throwing things out of the back, throwing a lot of mass at high velocity out of the back, and that momentum is going in this direction, and then it's taking an equal and opposite force in the opposite direction, allowing it to move forward. And now I think the reason that a lot of people confuse Newton's third law is because a common example here would be pushing against a wall, and we did this as well. So if you push against a wall with a force, you notice that the wall does not move. So we're tempted to say, oh, it's a balanced force. Nothing is accelerating. Just be careful here, because there's more than just one action-reaction happening. The reason nothing accelerates is if this blue dot represents the person, and let's switch to black for the wall. I'll draw that one over here. The person pushes on the wall. Force, person. The wall pushes on the person. So force, whoops, that's not level. Force, wall. Sorry, my paper's a little curved here. And according to this, right now, they should both be accelerating. They don't, but that's because there's another interaction at play. The push on the wall is canceled out by the interaction of the wall and the ground, so some sort of friction force. Same thing with the person. There's a friction force between the person and the ground that acts to oppose the other force. So there's actually two action-reaction pairs when you push against a wall. That's why a lot of people are tempted to say, oh, they cancel out, they're balanced. No, one set of action-reaction pairs acts in this direction, the other acts in this direction, and they're all equal. So the combination will balance out, but not the individual ones. Push hard enough, of course, and you might notice that, especially if you're wearing slippery shoes, things that don't have much grip, push hard enough, you might notice you start to slide backwards. That's because the friction force that's holding you in place is not strong enough to overcome your own push against the wall, and so you'll slip and start pushing yourself backwards. Alright, moving back to our review packet over here. Some Newton's second law problems. You plug and chug into the Newton's law formula. Acceleration is force divided by mass. 25 divided by 100 is 1/4, or 0.25, and this is meters per second squared. The momentum of an 80 kilogram runner moving with speed of 2.5 meters per second. Momentum is just inertia that's moving. So inertia is your resistance to change in motion when you're not moving, but if you get your inertia moving, then that velocity also resists change, and so they combine to form this thing called momentum. So you multiply together 80 times 2.5, and that comes out to be 200, and the units for this are just a combination of our mass and our velocity units. So it's literally kilogram times meters per second, or we read it as kilogram meters per second. Finally, the weight on Earth with a girl with a mass of 30 kilos. Well, weight is the force of gravity, which obeys Newton's second law, just like anything else. The acceleration of gravity is something that we know. It's constant, it does not change, and we just call it g, 9.8. So the weight is mass times gravity, aka 9.8. 30 times 9.8 comes out to be a little bit less than 300. It is 294 newtons. Okay. Weight is measured in newtons. Yes, pounds are a measurement of force, but they are an English unit of force, not a metric unit of force. So none of your calculations on the test will be in pounds. You won't have to worry about converting between that. Tune into the next video for work, power, and machines.